A comet rounds the sun on a long curving arc. To find the work gravity does on it, you'll face a line integral, force dot displacement summed along every bend of the path. That sounds hopeless. It is not. Gravity is a central force, and for a central force, the whole curved path collapses to a single integral along the radius. In this video, we evaluate that integral for the sun's gravity and for the electric force between two charges. Then add the three coordinate directions together to reach the work-energy theorem in 3 dimensions, and its rate form, power. Set up polar coordinates in the plane of the motion with the origin at the center of force. Any small step the body takes splits into 2 pieces. A radial piece, dr in the direction r hat, and a sideways piece, rd theta in the direction theta hat. A central force points purely along r hat. Dot the force with the displacement, and the sideways piece dies because r hat dot theta hat is 0. What survives is dw equals f sub r dr. That is the whole trick. The angular motion, however complicated, contributes nothing to the work. The line integral over a curved orbit collapses to an ordinary one-dimensional integral of the radial force component, from the initial distance r sub I to the final distance r sub f. Here is the first example. A body of mass m moves in a fixed orbital plane about the sun, whose mass is m sub s. It starts at a distance r sub I from the center of the sun and ends closer in at a distance r sub f. The question, how much work does the gravitational force do on the body along the way? Treat the sun as fixed and put the origin of the polar coordinates at its center. The gravitational force on the body is the inverse square law. G times m sub s times m over r squared, and it points along minus r hat inward toward the sun, because gravity attracts. From the previous frame, the infinitesimal work is the radial force component times dr. So dw equals minus gm sub sm over r squared times dr. Integrate from r sub I to r sub f. The antiderivative of minus 1 over r squared is plus 1 over r, so the work equals gm sub sm over r. Evaluated between the limits. Gm sub sm times the quantity 1 over r sub f minus 1 over r sub I. Now check the sign. The body moved closer to the sun, so r sub f is smaller than r sub I, which makes 1 over r sub f the larger reciprocal. The bracket is positive, so the work is positive. That matches the physics. The force points inward and the body moves inward, so force and displacement agree, and gravity feeds kinetic energy into the body, the same sign as a stone falling toward the earth in a uniform field. 2 observations before we move on. First, the answer depends only on the 2 radii, not on the shape of the path between them. Second, if the distance does not change at all, a circular arc, the work is 0 because the force stays perpendicular to the motion. Second example, same geometry, different force. 2 point-like bodies carry charges q1 and q2. Body 1 is fixed in place and the body 2 is free to move in an orbital plane. The question, how much work does the electric force do on body 2? Put the origin of the polar coordinates at the fixed body, body 1, so r measures the separation between the charges. Coulomb's law gives the force on body 2, 1 over 4 pi epsilon naught times q1 q2 over r squared along r hat. Notice there is no built-in minus sign. The sign lives in the product of the charges. Opposite charges make the product negative, so the force points inward. Attraction. Like charges make it positive, so the force points outward. Repulsion. Gravity never offered that choice. The central force collapse applies unchanged. dw is the radial component times dr. Integrate from r sub I to r sub f. The antiderivative of 1 over r squared is minus 1 over r, so the work equals minus 1 over 4 pi epsilon naught times q1 q2 times the quantity 1 over r sub f minus 1 over r sub I. Now work the 2 cases, opposite signs first. The product Q1, Q2 is negative and the force pulls body 2 inward, so left to the force alone it moves closer. R sub F is less than R sub I and the bracket is positive. Leading minus sign, negative product, positive bracket, the work comes out positive, same signs next, the product is positive and the force pushes body 2 outward. So the natural motion is apart. R sub F exceeds R sub I, the bracket is negative, and the leading minus sign flips it. Positive work again. That is the pattern to remember. Whether the force attracts or repels, a body moving the way the force pushes it receives positive work. The electric result differs from gravity only by a constant and a sign convention. The physics of natural motion is identical. Now zoom out from particular forces to the general theorem. Recall the one-dimensional argument. Start from m times the integral of a sub x with respect to x. Write the acceleration as dv sub x over dt. Then regroup the differentials. dv sub x over dt times dx is the same as dx over dt times dv sub x, and dx over dt is just v sub x. The integral becomes m times the integral of v sub x dv sub x, which evaluates to 1/2 m times the final x velocity squared minus 1/2 m times the initial x velocity squared. Newton's second law, F sub x equals ma sub x, turns the left-hand side into the work along x. The integral of f sub x dx equals the change in 1/2 mv sub x squared. Nothing in that argument cared which axis it ran along. The same chain works in y and in z. The integral of f sub y dy equals the change in 1/2 mv sub y squared, and the integral of f sub z dz equals the change in 1/2 mv sub z squared. Add the 3 equations. The left-hand side becomes the integral of f sub x dx plus f sub y dy plus f sub z dz, and that sum is exactly the scalar product of the force with the displacement, integrated along the path. It is the work W. The right-hand side collects into 1/2 m times the sum of the 3 squared final velocity components, minus 1/2 m times the sum of the 3 squared initial components. The sum of the squared components of velocity is the speed squared. So the right-hand side is final kinetic energy minus initial kinetic energy. There it is. The work energy theorem in 3 dimensions, the integral of f dot dr from the initial state to the final state equals k sub f minus k sub I. Positive work speeds the body up. Negative work slows it down. Zero work, like gravity on a circular arc, leaves the speed unchanged. And note carefully, the theorem governs speed, not direction. A force can bend a path all day without doing any work. One more step, the rate at which the work is delivered. In one dimension, instantaneous power was force times velocity, f sub x times v sub x. The 3-dimensional version follows straight from the work element. Power is dw over dt. Substitute dw equals f dot dr and divide the displacement by dt. Displacement per unit time is the velocity, so power equal f dot v, the scalar product of force and velocity. Power is also the rate of change of kinetic energy. Write kinetic energy as 1/2 m times v dot v. Differentiate with the product rule for scalar products. Both factors contribute to the same term, so the 1/2 cancels, and the dk over dt equals m times dv over dt dot v. But m times dv over dt is mass times acceleration, and by Newton's second law, that is the force. So dk over dt equals f dot v, which is the power. The 2 statements are the same physics. Integrate the power over time, and you recover the work energy theorem. Differentiate the theorem, and you recover the power. Put the whole picture together. Work in 3 dimensions is a line integral, force dot displacement accumulated along the path. For a central inverse square force, the integral collapses to 1 dimension and evaluates in a single line. For the sun's gravity and for the Coulomb force alike. And in every natural motion, attraction pulling bodies together or repulsion driving them apart, the force does positive work. Summed over the three coordinate directions, the same integral equals the change in kinetic energy. The work energy theorem in 3 dimensions. Differentiated in time, it becomes power, F dot V, the rate at which kinetic energy changes. One line integral, 3 phases, a number you can compute, an energy bookkeeping law, and a rate. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.